I just had to get the last little thing set up there. Hi, everybody. Welcome back to Chem 140. What are we doing tonight? We are doing... This might be the shortest lecture of all of them, because Units 4 and 5 are like 11 slides total. I didn't write the textbook, but I wanted to keep aligned with the textbook that we used to use, or that we use for 140. But that's in an in-person class, and I don't require it because I have this OER thing that sort of is its own just textbook online that you can use. So, but what the text does is it puts these two things into their own units, and they're important topics, but I guess they don't really go anywhere. Like, you can't really put them in the calculation section because they're just too different. Like, you could do that with density, but density is important enough that it needs a little bit of a different discussion. And then temperature is just like, where the hell do you put temperature, right? So we're going to talk about that, and then we're probably going to do a little bit of chapter 6, but we'll end early tonight. So I do want to talk about density. That's what we're going to start with. And I'm going to show you a few videos, and we're going to do a bunch of calculations so that you can just play around with it. The lab that you're going to be doing for week 4 is all about density, and so we'll talk a little bit about that too. As for things that are coming up and are due, so quiz number 1 is last call is tonight. So if you have not done it already, do that by midnight because it will close. If you don't get it in by the deadline tonight, I don't accept it. So make sure that you have finished that by the deadline of the evening of this lecture. If you're watching it in the future and you're like, shit, I didn't do quiz 1, probably too late. Make sure you do it before last call ends. Lab worksheet number 1 is also due tonight, so make sure you get that in and uploaded. Last call for that will be tomorrow. You will get an email about that. You should actually be getting an email right now about the last call for the quiz number 1. Let me just check to make sure that that's true, because I told it to do that. Yeah, there's the email. Okay. I pre-program all the assignments so that when I put them up there, I also make it post an announcement for last call at around 5 p.m. on the day of last call. So you should get that. And then quiz number 2. Quiz number 2 is due next week on Monday the 26th. Quiz number 2 is for Unit 3 only. And because Unit 3 is like crazy calculations, the unit, you get extra time. So the quiz will be slightly longer for Unit 3. For Unit 3, yeah. Quiz number 2 will be slightly longer. Okay. With that all out of the way, I'm on the wrong screen. So there we go. I'm on the right screen now. Let's talk about density. What is density? Density is a ratio of how much stuff something has in a given volume. If you have ever held something made of lead, or maybe of like tungsten or something. My dean, I don't know if you know Al Friedman. He used to be my dean. Now our dean is Drace Belcher. I haven't actually met her yet. But I don't know if she has a cube on her desk, but Al did. Al had 2 cubes. One was aluminum and one was tungsten. And he would always joke to students that came in to talk to him, like, yeah, pick up the aluminum cube. And you pick up the aluminum cube, and it fits in your hand, and it's really light because it's made of solid aluminum. And then he hands you another cube that looks exactly the same, but it's made of tungsten, and then your hand hits the table because it's like 12 times heavier for the same volume. And so that's a great example of density. An object with a really high density will feel super heavy compared to how big it looks. Lead is really famous for this. If you had like a lead paperweight, I grew up in a family of rednecks, so my family would load shotgun shells using lead shot, and the little bags of lead that you would have were just like, it's these little tiny bags, but they're just so heavy for how big they are. Likewise, if you filled one of those bags instead of with lead, you filled it with like feathers or something, then it'd be ridiculously light. The bag would weigh more than the contents, really. So density has a very wide range of what it can be, and we represent it using this formula. So the density of an object is going to be its mass divided by its volume. There are many different ways to express density in terms of their units. You could put different things in for mass and different things in for volume, but the standard ones are as shown here. Whenever we work with solids, we're going to express their densities in grams per cubic centimeter, because a solid is pretty easy to make a cube out of. I'm just drawing a cube real quick here. So, like, I could prepare a metal cube out of this. Does density have to do everything with how the molecules are arranged? It does, actually, but that's not the only feature. So, there are different ways you can arrange molecules that are more efficient. You could do this as an example. Like, if you had a bunch of golf balls and you stacked all the golf balls directly on top of each other without allowing them to fall into, like, the little crevices between, you would notice that, oh, there's these giant holes between all the golf balls. Then if you let the golf balls, like, settle more naturally, like, they would make little triangles, and then a fourth one would sit on top of a triangle of 3, because it would fit in that little divot. I'm trying to, like, describe this picture. That would be more efficient. And so if you could get more golf balls into, say, a box, there would be more golf balls in it, and thus it would be heavier. So depending on how you pack the atoms in there, and all different atoms pack in all different ways, we'll talk about that very briefly, I think, at 162. That increases the density. The other thing that affects it is also the mass of the atoms. So some atoms are just heavier than others. For example, lead is very heavy because it has tons of protons and neutrons in its nucleus, whereas something like helium has only 2 protons and then 2 to 4, 1 to 3, I guess, neutrons. And also it's a gas. So the state matters, how it packs, how big the atoms are. And yeah, you'll see it in physics as well. Now that all that discussion that we just had there is specifically for solids. So liquids are kind of weird because liquids can move around. It's hard to put them in something like a cube, right? Like, you can't have a liquid cube. It would just go and all the molecules would just expand in every direction, but still try and retain their volume. So we express liquids and liquid densities in grams per milliliter because a milliliter is just more convenient. But remember, this and this are the same thing, right? So if you report your solid with a density in grams per milliliter, that's still valid. Like, I wouldn't mark that wrong. Another physicist would be like, oh, okay, I understand what you're doing. The one that's different that we got to consider is gases. Gases have a density expressed in grams per liter, because if you express them in grams per milliliter, you get this really, really tiny decimal. For instance, I don't remember what the density of air is. I want to say it's like 1 gram per liter, but it's actually more like 4 or something, I think. Let me look that up real fast. Density of air, grams per milliliter, or grams per liter. That's what I want. Oh, it is 1.29 grams per liter. So if you ended up writing that in grams per milliliter, air would be something like this. And dealing with decimals that are that tiny is obnoxious. So we do this. We go, whoop, we'll put it over here, and then this becomes just liters. I should put the dot in there. There you go. So we just scale it up by a factor of 1,000. And that's pretty much the gist of density. So you're going to have this equation here on the board. And because it is a conversion factor, it relates mass to volume. We can use it in any place that you would be required to figure out, like, oh, what's the mass of this object if here's its volume? If you know its density, you can answer that question. Now, this is a fun fact about density, and everybody probably knows this, but the applications of this are as broad as lava lamps all the way to shipping freighters. So if you put multiple objects into a fluid, and those objects are allowed to sort, like, by sort, what I mean is they mix and either sink to the bottom or rise to the top. The objects with the lowest density go to the top, and the objects with the highest density go to the bottom. And I've shown this video like 74 times. I don't know if I've shown the density column to you guys yet. Have we seen the density column? Let me know if we have. while I'm loading this. It's playing the awful music. So I'm going to show you the density tower here. However, I am not captured in the right spot, so hold on. Let's see here. Yeah, that didn't line up correctly at all. Oh, that top part did, though. That was a pretty good guess. Okay. So I'm going to cover up the chat real quick. And then also me. And we're going to talk about this density tower. So here, enjoy the awful music with me. Here is what you need. Here's all the things we're going to sort, besides the vase, which is what we're going to put the stuff in. You do not need adult supervision. Don't worry. Here are all the things that we're going to sort. I'm going to hit pause here. So these are the liquids that we're going to put in the density column. And they're arranged from left to right, from highest density to lowest density. And they're also arranged in such a way that we don't get two things that mix together. So for instance, water here and rubbing alcohol mix completely. We don't want that. We want to have them separate. So we put vegetable oil between them. Not only because its density is between them, but also to prevent water from mixing with rubbing alcohol. Then we're going to put them in the column. Here we go. Go slow, slow. And then we're going to drop in all those solid objects that were listed at the beginning. And so you could see that some of this will try and mix with the other layers. And, like, that's fine. We don't really care about it. But the layers remain intact. And what happens is when you drop something into it... I'm going backwards here. So we're going to drop this tomato in here. Notice that it doesn't sink all the way to the bottom. It just falls. And then it gets to a point where it stops sinking. Because it, too, is being sorted by its density. So solids that we're dropping in here also end up sorting into wherever their density is. So the density of the cherry tomato must be higher than that of this right here, which I believe is... Well, this is the vegetable oil. It'll show in a second. The green one's water. And it makes sense that a tomato, being mostly water, but also other stuff in there, should have a higher density than water. So it sinks below that, but not below the next thing. Does viscosity matter? It does not, actually, because something can be viscous, and that'll just slow down the rate at which it sorts. Just the density matters. So here's the rest of the objects. And they slowly sink to the correct spot. And then we got a ping pong ball, because it's full of air. There's all the objects. And so these have been all sorted based on their density. So the thing that was made of metal at the bottom sank all the way to the bottom. That checks out. The plastic dice, or I guess it's one, so the plastic die, is more dense than milk, but less dense than maple syrup. The tomato sunk below the water level, but it floats on the dish soap. There's a soda cap, which I don't know what they put in the soda cap. I would have thought the soda cap would sink pretty far, because it is a metal too. But the ping pong ball here, ping pong ball is just full of air. You drop it in, it doesn't even try to sink. It floats on the top. So yeah, there you go. There's a density column with all these things in there. So we can get rid of that. And I can never play that video again this quarter, thank goodness. I'm teaching 3 different introductory classes. That's the 3rd time I've showed this stupid video, and I can't stand that music. It's just so bad. All right, let's do a practice calculation just to get you familiar with how to use the density formula, because this is like the most basic thing. I'm going to give you olive oil. I'm going to give you 18.6 grams of it, and then we weigh that sample, and it has, we put it in a graduated cylinder, and its volume is 20 milliliters. What we're going to do is then pour that into a beaker that has 25 milliliters of water, whose mass is 25 grams. Where will the oil go? Will it sort to the top, or will it sink to the bottom? So you can probably just tell by looking at the calculation, but do the actual calculation, get the density for both the olive oil and the water, and then draw a little picture of a two substance density column. I'll give you like a minute to do that, and then we'll do the answer on the screen. All right, I had to go and get more water because I had just finished that. My addiction to seltzer water. I make a lot of aluminum waste, unfortunately. Thankfully, aluminum is recyclable. All right, so let's calculate the density of these two substances real quick. So if I calculate the density of the oil, that would be its mass divided by its volume. And you'll notice that the units don't cancel out, so we're going to keep both of the units there. That's not my calculator, that's my phone. So what do I get when I do this? I get 0.930. It doesn't sound like it, but I'm not drinking beer during class. That's for after class. All right, let's do the density of water. Now, obviously, the mass and the volume are the same. So I'm just going to get 1 gram per milliliter. And so what we would say is, oh, okay, well, the density of the oil is less than the density of water. So if I were to draw a picture of it, I'd have 2 layers, and the oil would go on the top, and the water would go on the bottom. So we can make a 2-component density column using oil and water, and this is how they would sort. Now, it doesn't really matter where this line ends up. For example, I could use as much of the oil as I wanted to, and I could have this huge layer of oil and it still floats to the top. But the opposite is also true. If I had a very small amount of oil, it would still float to the top. So regardless of which component there is more of, the density will remain the same because as I add more volume, I'm also adding more mass, and the ratio remains constant. So wherever these layers end up being, they will always sort in this fashion. So there you go. That's the basics behind density. All right, let's do some more complicated problems with this because you're going to see more complex stuff as the quarter goes on, because we use density as sort of just it's a useful reference factor because the density of a substance, provided you're at the same temperature when you measure its density, is relatively constant um, given extraneous conditions. So like pressure can change it slightly, um, but you need a lot of pressure to do that. So for our purposes, density is roughly a constant. So, for instance, let's look at the density of ice. At 0 degrees Celsius, here's its density, and this is reliable. So, if I have a glacier that has a volume of 35,720 liters, what's the mass of the glacier? So, you could measure how much ice something has by just its displacement in the water. So, if I could submerge the glacier, for example, I could see, oh, it displaces this much water. Now, obviously, you can't just reach up and go bloop and push the glacier into the water. So this problem isn't super practical, but it's a good exercise. So what we're going to do is we're going to calculate the mass of the glacier based on this information as shown. Now, there's two ways to do this. You have this formula right here, yeah? So if you identify what parts you have, well, we know the density and you know the volume. You could just rearrange the formula, do a little bit of algebra, multiply both sides by v, and you get the answer. Now, how does buoyancy complicate things? So that gets into a little bit of physics that I can't really give you the answer to because I don't know the formula off the top of my head. So things are buoyant based on their density, and the closer the density is of two substances, the more it tends to sink. So like as you load a boat, for example, like if this is my boat, like this is a cross view of like I don't know, like an airship carrier or whatever. An airship carrier, an aircraft carrier. I'm playing too many fantasy games. So the water might be like right here, but as you put stuff on it or put stuff in it, then its density increases and this will slowly sink down and this water level will slowly go up. So the average density of the substance is related to the density, but in terms of like how much will get displaced, I don't actually know that formula off the top of my head. Yeah, it's something like that. I don't actually know it off the top of my head. I have to go look up the formula. But density is a important thing in there because you can calculate one thing and the other and so on and so forth. So we have this formula here, and I could just multiply these two things together and just get mass. But in reality, what you're doing when you're using this formula is you're just doing a conversion, right? I have a volume, and if I multiply by another volume, I'll just get the mass out, right? Because the volumes would then cancel. That's exactly what's going on right here, right? Density times volume is mass. So you don't actually need to use this formula if you just look at the units. So I'm just going to write down the numbers that we have here. And I'm going to multiply by the density. And you could see that this would kind of work, but there's an issue, and the issue is our units don't match, right? So this unit and this unit, I can't cancel those. So I need to do something with this first before I can make that cancel. And so what I would do is I'd say, okay, well, a cubic centimeter is the same as a milliliter. So now those go away. And then I can convert milliliters into liters by just doing this, right? So now those go away. And then finally, this one goes away with this one. So I can punch all of that in my calculator, and I'll get something like 35,000 kilograms or something ridiculous like that. Oh, well, this would actually give me my answer in grams. So I'd get 30 million grams or whatever. My calculator's not on. 35720 times 0.9167 divided by 1 times 10 to the minus 3. All right. So here's the mass it spits out in grams. I get 4 sig figs. So 3.274 times 10 to the 367. There we go. Now, that's not super practical to report the mass of something that large in grams. So maybe you'd want that in kilograms. Okay, well, we can do that in kilograms too. We'll just turn grams into kilograms so that these grams cancel with those. And then 10 to the negative 3 and 10 to the positive 3 would cancel out too. So then you would get this as your answer in kilograms. And that's a little more reasonable. On an assessment, I would tell you what units to give your answer in. But if it's open-ended like this, you can report it however you want to. Grams or kilograms would be acceptable here. Either of those is fine. All right. Any questions, let me know. So you're going to be given units that are going to mismatch like this, and so you will need to do the dimensional analysis, this part over here. Oops, I want to... that's fine, actually. So this part over here is just to make these units match up and get rid of the ones we don't want. Okay, so let me clear my text because now it will all appear on here. There you go. All right, so here's another mismatch of units here. So if this is the density of air, how big would a balloon have to be for the balloon to have 32 kilograms of air in it? Like, what would its volume be? So go ahead and give this a try. You're going to have to flip around the density and use it in a different orientation to get to the answer. Note that for volume, I'm not asking you for a specific unit for volume, so just give me whichever volume unit is practical or easy for you. So go ahead and try the calculation, do the conversion, type in your answer in the chat, and we'll go over it together in a second. 1 or 2 more minutes, and we'll go over the answer. All right. I was just setting up something else for our discussion of the lab later. That's not what I wanted to do. That's not what I wanted to do. That's what I wanted to do. Oh, everything is gone. There we go. Okay. We don't need the top part of this problem, so we'll just crop it away here. Okay. So I know that the density of my air is that, and I know the mass of my air is that. I'm going to use the mass to start. And then I'm going to take the density, and I want to cancel out the mass, so I need to put the mass on the bottom so that it would cancel out with this. Now, this unit and this unit won't cancel out because they're not the same thing, but this is where the numbers would fall, right? And if you ever have a blank like this, it's always per 1. So we just put a 1 there. But now I just need to get rid of this grams and turn it into kilograms. So I'm going to do that over here. We're going to cancel this gram out with kilograms so that this kilogram can then cancel with that one, and that's going to leave me with volume. And so I just say, oh, okay, a kilogram is 1,000 grams. Now I can get the answer because this is going to be the only unit that's left. So when I do this, I'll have an answer that's in liters. So I'd get 32,000 divided by 1.29. 32,000 divided by 1.29. And I get 24,806 liters, which I only get 3 sig figs, so I'm going to just do this. 24,800. There you go. I really should just put my calculator over here. Just put it on top of my phone or something. For some reason, I hit a graph. I don't even know what equation that is. What equation was I typing in there? Made this really cool curve. I just haven't used the graph function on my calculator for like 14 years. All right. So that's the volume of a balloon that has 32 kilograms of air in it. That's ginormous. That might be like hot air balloon large. I'm not quite sure if I can estimate how big that is, to be honest. All right. Do I have more problems for you to try? I do. Here you go. So if I have gold, and gold's density is 19.3 grams per cubic centimeter, what volume would 329 gold or grams of gold melt down and occupy? Second question, I have a carbonated beverage. Here's its volume. Here's its mass. What's its density? That's easy enough to do. Here's a ship that has this volume or this displacement. What is the maximum mass that it can have and still float in water if the water has a density of 1 gram per milliliter? Something to note, if you are making a seafaring vessel, and by seafaring I really just mean any body of water that has salt in it, salt increases the density of water significantly, so you can put way more stuff on your boat. We're going to assume that we're just floating it in like a bathtub of pure water. A bathtub that's 65 times 10, 65 million liters. So, like the biggest swimming pool you could imagine. So, go ahead and answer these 3 questions. We'll go over the answers together when we come back. So, type your answers in the chat for me when you get them. I made you do that calculation for nothing, right? Or you just look at it and know. Yeah, the third problem, you're just if you get a number, you're like, well, that's rude. Yeah, you've done it correctly. All right, 1 or 2 more minutes, we'll go over the answer. All right, let me play around with this real quick. So these are really straightforward problems. We're going to give you more practice at these in the laboratory that I'm going to talk about after we take a break. I minimized the thing. That's not what I meant to do. There we go. But also, where'd my pen go? There it is. But also, if you check out the worksheets for the chapter content, as well as if you have the workbook, there's extra practice in there if you need it. All right, so I have a 329 gram bar, and I know its density, and I want to solve for the volume. So I'm going to set up density such that the units that I don't want cancel out. And the density is 19.3 grams per cubic centimeter. Gold is really dense. I don't know if you ever had the opportunity to hold like a gold bar, but like, whoa. Really heavy. Hard to run away with gold. If you play RPGs for like pencil and paper, and you sort of just hand wave weight, like, because most of your currency is measured in gold coins, knowing something about how dense gold is really makes you wonder, why would you make a currency out of gold? Like, it's just so freaking heavy. You could barely carry anything. Although, I also think that currency in those games is completely undervalued, which makes the problem even worse. Like, you find a treasure trove of 20,000 gold pieces, and it's just like, geez, who could carry that? Nobody. Anyway. But yeah, that's what the bag of holding is for, exactly, right? So you don't have to worry about that. My fighter in D&D, which is he's actually in the math problems that you've probably encountered. Uh, Mani, the half-orc fighter, he has the bag of holding for the party because he is the one that carries all the shit. That's what happens when you're the only person with strength 20, is you become the person that holds stuff for everybody. And, like, that's fine. So 329 grams of gold would fit into a volume of 17 cubic centimeters, which is not that big. If you had a graduated cylinder, it would only fill up to the 17 line, and that's a third of a kilogram. So it's like, wow, that stuff's heavy. A third of a kilogram is almost a pound. So just some numbers that you can crunch there. So that's how we solve that problem. This one is just a simple density calculation. Here's the mass, here's the volume, tell me the density. Okay, well, I could do that. 355 milliliters, by the way, is the common volume for soda. It is 12 fluid ounces, but imperial units are silly. So we use grams of milliliters. There you go. That'd be the density of this beverage. That's probably a common, like, moderate sugar soda, I would say. If you're in 161, you will be calculating the sugar quantity in beverages based off of their density as well. Why did the 329 go where it did? So let me get the problem back on the screen real quick. So for the first oops, that's the wrong one. There we go. So I was given a mass and a volume, or in a density. So I know these two things. And density is always kind of your conversion factor, and you can flip it around however you want to. Actually, let me do that in a different color here. You could flip this around however you need to solve the thing. So what I do for these density problems is I start with which of these I know and solve for the other one, and then just orient density however I need to. You can't see half of that because the problem's in the way. Oh, you can. Never mind. It's fine. So, yeah, if you're given a problem like this and the problem is not calculate the density, but calculate this thing given the density, pick which one you have, start with that, and then put the density in the correct orientation, and you'll be able to solve for it. And then this is my douche problem, because you're going to get the same answer that you start with, and that's intended, actually. But yeah, you have, so here's the volume in liters. And I'm going to make you do all this dimensional analysis to get a mass. And when you get back to kilograms, you're like, oh, it's the same number because you're dividing by 1, right? Or you're multiplying by 1. So let's put the density in. And then I got to make this unit match up with this unit. So I'm going to go milliliters here, liters here, and then a milliliter is 10 to the minus 3. So now you would get 65 times 10 to the 9 grams. But if you wanted to do this in kilograms, then you have to put grams here and kilograms here to cancel those. This step's actually optional. But if you do it this way, 10 to the negative 3 and 10 to the positive 3 multiply together to give you 10 to the 0, which is just 1. So now you have 65 times 10 to the 6 times 1 times 1 times 1 times 1 times 1. And so you just get the number back. And of course, that should probably make you grumpy. All that works to just get the same number. But what that does tell us, interestingly enough, is that when you have something in grams per milliliter, that's the same as this. Because really what I'm doing is I'm multiplying this one by 1,000 to get to liters. And then I'm multiplying this one by 1,000 to get to kilograms. And then those thousands cancel out. So if you find a density in kilograms per liter or grams per milliliter, you'll get the same number. What do we got here? Oh, now we're in temperature. Okay, so what we're going to do is we're going to take our break. So let me just put this here. I'll put this here. That's wrong. That's the one I want. Oh, break is over. Hold on. Boop. Boop. There we go. We'll get the music back on real quick. And I can't find the right window. There it is. Okay. So we'll start this. And I'll see you in just a little bit. So see you in 10 minutes. Hi again. Welcome back. Let's wind the music down here. So, before we talk about temperature, because temperature is like a 10-minute thing at most, I do want to talk about the lab. And that's not the screen that the lab's on. That's the YouTube analytics. Let's see here. So I want this. That's gonna be sized wrong. Hold on. All right. So lab number 2. So let me get the first window up here. Oops, that's the wrong button. And oh, I guess hold on. This is gonna barf for a second here. Yeah, that didn't work. Hold on. There we go. I can't actually capture 2 of the on the same window, so I have to actually get a different window here. This one. Yeah, there we go. And so now if I do this, that almost works. Oops. I guess we kind of need the top part. Okay, so here's the worksheet for lab number 2. I do need the bottom of this, so I need to... Yeah, I don't know how far down this goes. There we go. Let me get all that on the screen here. Okay, so I'm covering up everything. But I can't put this one on top. So what I can do is that. There we go. Okay, so let me Alt-Tab to the correct thing here. Okay, so this is the assignment for lab worksheet number 2. Lab worksheet number 2 is just density and various applications of it. So it goes over a introductory little blurb about density. I have this table here, which is the density of water at various temperatures from 15 to 46. You're going to need this for like one question, but it's intended to illustrate that density is a function of temperature for all substances. For liquids and solids, actually, I guess all states that matter. As temperature goes up, density tends to go down. And the reason for that is because as objects gain kinetic energy, which is what temperature is, they tend to move faster and farther apart. And so whatever forces are holding them in place tend to relax a little bit because the forces can't hold the molecules that are vibrating. I'm vibrating here just to like illustrate it. You can't see that. And so this is really common with things like, say, steel. So like steel, when you are making things like railroad beams on a railroad track, the expansion of steel on a really hot day is a serious engineering concern because if the steel is lined up too close to each bar is lined up right next to the other ones on like say a cold day, and then it gets really hot from like say baking in the heat on a summer day, then what will happen is those bars will try to expand, and if they have nowhere to go, then they buckle, and that's a problem because a train can't go over a buckled steel bar; it will derail. So we have to consider things like how does density affect the shape of objects that are solids, or what happens when liquids change density, and so on and so forth. A less extreme example of this would be if you've seen those temperature column things. Let me close this real quick while I'm doing a search for it. So like density temperature column. I'm trying to find specifically. I don't know what it's called. Maybe density thermometer. Yeah, here we go. It's these things. So maybe you've seen these things before. That's a fine capture. Apparently it's called a Galileo thermometer. And so the way that these work is that the density of water and also all of the liquids that are in those little baubles in there changes as temperature increases or decreases. And what ends up happening is that water changes more than the substance inside, and as things heat up, the density of water changes, and then things will either rise or sink based on how it's set up. I don't remember which way it's set up. I want to say that as it gets hotter, more of them fall down because the density is lower and only the lightest thing can float, or the thing with the lowest density. So there's that. So that's an application of density that you may have seen before. When I worked at Tacoma, they had one of those in the laboratory, and it was kind of cool. The worksheet. Where do I find the video with the actual... Oh, for lab number 1. The video is in the documentation. So if I go to here, this will pop up lab worksheet number 1. Sorry, give it a second here. If you scroll down, the video is in this document. It's right here. There it is right there. So that's that video for lab number 1. So for the density experiment, you're going to do 4 parts. And so if I go back over to this thing, I'll just plop that one back on top here. What you're going to see is down at the bottom, there's experimental part A, part B, part C, and part D, and also analysis questions. I've separated this into the 4 parts that are the 4 experiments that you're going to do. In part A, you're going to answer questions. In part C, you're going to do some calculations, and then in part D, you're going to do more calculations. So this is all just like, oh, let's use information based on stuff that is in the documentation. No big deal. Part B, though, is special because you're going to make a graph. And so we need to talk about how to make a graph. So I'm going to make this a little bigger so it fills the screen. How do you make a graph? What you're going to do is you are going to calculate the density of various solutions of isopropanol. So I have a 25% isopropanol solution, a 50%, 75, and 100%. You're going to calculate their densities. And then you're going to calculate the density of an unknown solution based on this data. The unknown can have any percentage of ethanol, not ethanol, sorry, isopropanol in it between 0 and 100%. And what you're going to need to do is figure out what that percentage is and report it right here in this box. Now, how the heck do you do that? What you're going to do is you're going to make a data table. So first you want to plot density on the y-axis and then percent of isopropanol on the x-axis. So I'm going to report that right here. So we'll say percent isopropanol. I'm just going to call it IPR because that's the abbreviation that inorganic chemists use. And I'm an inorganic chemist, so that, and then we'll do density. And we'll do grams per milliliter. Okay, so I'm going to just put these numbers in. So I'm going to say 25, 50, 75, 100. And then I haven't actually calculated the densities, but I'm going to just make up some numbers. So we'll say 0.900, 0.825, 0.774, I don't know. There, that's good enough. You're going to notice that one of my numbers kind of got truncated. So I typed in 0.900, but Google's like, oh, you don't need those zeros. But we do need those zeros. If you ever run into that issue with any cell, here's how you fix that. Up here at the top is a button that says increase decimal places. You can increase this to have as many zeros as you want, or as few zeros as you want. And if you go too few, what it will do is it'll start rounding. It keeps the number that you've written in there. You can see it says 0.9. But what it reports is, oh, I'm going to round that to 0 decimal places because that's what you selected. I want more decimal places than that, so I'm going to input them manually by clicking these two buttons up here, okay? So that's how you do that. I know a lot of people get stuck on that because they type in a number and then Google eats their 0. And like, what the fuck do I do? And the answer is, it's this button right here. This button right here will let you format it in different ways. I would just use these two buttons over here. But if you know how to use Excel, you can format something as a number or plain text or whatever. Okay, so now I've got my data. I need to make a graph out of it. And so I have the directions for making a graph right here. You're going to put your graph just directly on the directions. But I'm going to show you how to do this first. So don't select anything, just click somewhere. And then you're going to go up here to Insert, Chart. And a window is going to pop up from the side, which you can't see because I haven't captured it. I got to make this smaller, don't I? Oh, boo. Okay. Okay. There we go. Unfortunately, that's as big as I can get it to show everything on the screen here. Here's your graph. We're just going to put the graph directly on the directions because I know what the directions are. The first thing you want to do, you want to select a scatter plot. You will always make scatter plots in chemistry. Don't make any other type of chart. They are all worthless. We need a scatter plot because we're going to try and derive a relationship out of these. And in order to get a line of best fit, we need a scatter plot. Then what it's going to do is it's going to ask you, okay, what do you want your x-axis to be? So you're going to click Add x-axis. And if you click this button right here, this little grid, it'll let you select a data range. So I'm going to go select a data range, and I want this to be my x-axis. It's going to plot what that command would be. You could type in the command manually, but just really select it. There you go. And then down here where it says series, you're going to add the y-axis. Boop, there you go. And there's your graph. Now, you'll notice that my graph starts at 25 because the first data point that I have is 25. Maybe you want there to be a 0 in there just so it's a little more clear. So the way that you do that is you go over here where it says Customize. And over where it says series, no, not series, sorry. Horizontal axis. We're going to change the minimum. We're going to make it 0. And that just changes your graph. There you go. Now, all good charts need titles. So we're going to give it a title. So the title will be, this is a sample graph. There you go. And then I'm going to call my axes something. I don't see where to enter that. Oh, I click right here. So the horizontal axis will be, this is the x-axis. I'm just typing in random shit so that you see how this works here. And then this is the y-axis. Obviously, you're going to label these with things that are more relevant. So, like, I would label the x-axis percent isopropanol, and the y-axis would be density. You want to plot density on the y-axis and isopropanol on the x-axis, because the convention is that you plot the dependent variable on the y-axis and the independent variable on the x-axis. In this case, density depends on how much isopropanol there is in there, but it's not the other way around. Isopropanol percentage does not depend on what the density is, because I could freeze the solution or put other stuff in there, and that would change its density too. But it would not change the amount of isopropanol that's in there. Okay, so one direction will be more relevant to what the other thing needs, and that's the thing that you should plot on the x-axis. So in this case, that's isopropanol. Now that I've done that, I accidentally clicked this away. Can I double click and get it back? There it is. Okay. So the next thing that you want to do is you want to go to series, and you want to go down here where it says trend line. And what this is going to do is it's going to take your data and put the best line it can through your data. And so now that's shown on the graph. So here's your trend line. You can see it there. Now, a line by itself is not super useful. So what we're going to do is we're going to, down here where it says label, we're going to include the equation. So this is now the equation of that line. Negative 2.59 times 10 to the minus 3rd, 10 to the minus 3, sorry, times x plus 0.962. All of that is your equation. So this is y equals this equation right here. The last good thing that you should do on a graph, you should always include this, where it says show r squared. R squared is a statistical function. And what r squared does is it tells you how linear your data is. The closer r squared is to 1, the better your data conforms to this line. Now you can see that my data doesn't perfectly fit the line. Some of the dots are a little high and some of the dots are a little low. That error is run through a statistical formula. I think it's the least squares formula, which is why it's r squared. And it gives you a value between 0 and 1. 1 means everything is on a perfect line. Your equation perfectly models your data. R squared equals 0 means no line you draw through it models your data. And your R squared will be somewhere in between. In the laboratory, in chemistry at least, you're shooting for R squared of like 0.95 or higher. It's hard to get lower than that without totally screwing up. But in a thing like statistics or social sciences or something like that, if you take so many data points, you're going to get R squareds that are not that high because people have varying opinions on things or they have varying qualities, and it's hard to find relationships that strictly relate, like a person's weight versus their age. Like, that would be a hard relationship to make a linear graph out of. So you'd have a low R squared with that. But for something like this, where we're measuring properties that are well understood and known, our lines tend to have very high R squared values. They'll be close to 1. Once you're done with that, you could just then resize the graph however you want to. And there you go. That would be that's basically what you do for part B. Is you're going to make a little data table on the left somewhere over there in that space. And then you're going to put the graph over here with the title, label your axes, make sure your equation is shown, make sure the line of best fit is shown, and so on. If you ever need to get that config menu back, just double click on the graph and it pops right back up. All right. Now, just because your graph is there does not mean it's fixed in stone. I can now change these numbers. So I can make this 30. I can make this 55. So if you make a mistake, oops, I don't know what happened there. So if you make a mistake in your graph, like, oh, I typed this number in wrong, that's okay. Go edit it, and it will edit the graph appropriately. Now, notice that by moving that data point way down here, my line is no longer very good, right? So, and if you just want to play around with it, like, I don't know, you could just do this. Like, now my data doesn't even fit on the graph. It's just ridiculous. Google Sheets will try and follow whatever it is that you're punching in there, and it will do the best that you can. But remember, you can control all this by just double-clicking and then going back and finding the option that changes that. Most of the changing stuff is in Customize. All right. So if you erase all of your data, the graph doesn't know what to do, and it does this. And if you just don't want the graph anymore, you just hit delete on it, and it'll go away. There you go. That's part B. Parts A, C, and D are just calculations. One thing I do want to point out is that the density of aluminum is used for part C and D. It's right here. I can make it bold for you. You're going to use that number in part C, but also you're going to use it in part D because you're going to know a bunch of things about your aluminum foil, except mysteriously not the density. Well, anything made of aluminum will have the density of aluminum. So just refer back to its value right here in part C and use that number for part D. All right. There is one more thing that I do want to talk about real quick, and that is just for part D. Parts A through A, B, and C are pretty straightforward, except for making the graph. But part D, I'm going to ask you to do something interesting. I want you to tell me how thick aluminum foil is based on the measurements that I gave you. So I cut a piece of aluminum foil, and I made those measurements, and then I threw it on the balance, and I got those numbers for you. From that information, you can tell me how thick it is using the following idea. And so what I'm going to do is I'm going to close this real quick and go over here. We'll talk about it a little bit. All right. So aluminum foil is really just a rectangular prism, right? So there is some length to it, and there is some width to it. And its area would be length times width. But there's also a thickness, which I'm going to call T. Now, if this was a rectangular prism, the volume of this aluminum foil would be the length times the width times the thickness of it. And that would be a volume in cubic centimeters, right? Well, we also know that density is equal to mass divided by volume. And I could say, well, hey, if volume is just this right here, this expression then becomes density equals mass over volume, length times width times thickness, right? Now, if the density is aluminum, or I'm sorry, if the material is aluminum, you know the density of aluminum because it's on that chart that I just showed you in the lab. You also know the mass and the length and the width because I measured those. So you can then solve for the thickness, which will require a little bit of algebra for you to do. But you should be able to determine how to calculate T, given all those other things, by multiplying both sides and dividing by both sides and doing whatever you need to do to manipulate the equation. So when we go back to the this screen right here, and I put this back on the screen, yeah, here we go. It looks like it's already done that for you. So it shows you the formula on the screen there right here. So now you can calculate the thickness. The units of the thickness will be dependent on what the units are in this expression, though. So if mass is in grams, length and width are in centimeters, and density is grams per cubic centimeter, thickness has to fall out in one of those units that's there. And you can do that by just doing the dimensional analysis, canceling out everything. This document just tells you all of these things. I have already put all these numbers that are in my funky comic book text already are in the Google Sheet. So you should be able to do all of the rest of this stuff on your own. And then you have some analysis questions at the end to answer. Okay. There are a lot of questions. This lab is way more involved than the first one, which was watch a video and report the colors. So don't dawdle on this one. It will be formally assigned next week and then due week 5. But you also have an exam at the end of week 5. So don't leave this to the last second and then be like, shit, I have to study for the exam, because there are a lot of calculations. But because we've now done the density part, I felt like, hey, let's just do the lab discussion today. So there you go. Any questions, let me know. Let's do the temperature lecture. The temperature lecture is entirely meant to be goofy, and this is 5 minutes long, and we'll finish it up, and we'll call it a day. So, what are the units of temperature that we use in this class? Here are the 3 temperature units that are familiar with you. There's a space in the middle. We'll talk about that in a second. Of these 3 temperature units, Fahrenheit is the one that we use in America. Fahrenheit is entirely used for one purpose as far as I'm concerned, and that is to confuse Canadians and people who live in other parts of the world that use civilized units like Celsius. The original intent of Fahrenheit, my understanding, is that 0 is really, really cold and 100 is really, really hot, and you want to be somewhere between those. And that 100 is approximately human body temperature. But though the human body is not a great rubric to base a temperature scale on, because what is cold to me is not the same as what is cold to you, particularly if you grew up in Alaska and I grew up in Southern California. I grew up in Central California, but I spent a lot of time in Southern California. In Southern California, 70 is cold. Up here, 70 is like, holy crap, that's way too hot. So, not a great temperature rubric. Instead, what we use is Celsius. Celsius is based on water. So right here, 0 degrees is the freezing point. Oops, I wrote the wrong thing. Zero is the freezing point. I'm writing it in the wrong spot. And now I have the wrong pen. There we go. There we go. Freezing point of water. And 100 is the boiling point of water. I've never been to Palm Springs, believe it or not. I've been down there around in that area, though. So I went to UC Irvine. So I know all the area around Irvine, LA, Riverside, etc. But I never went as far east as Palm Springs for whatever reason. Oh, well, I mean, the reason would be I didn't have a car when I lived down there when I went to college. So these numbers are a more useful tool to base our temperature off of as scientists. So we use Celsius. Celsius is a more useful temperature scale. And also, we have this other scale over here, the Kelvin scale. So the Kelvin scale is actually special in the sense that the number of gradations between freezing and boiling for Celsius and Kelvin are the same. So that's useful. 1 Celsius and 1 Kelvin are the same thing. But also, we've set the 0 point for Kelvin at a very specific temperature, and it's called absolute 0. We're going to talk about absolute 0 more in 162 when we talk about gas laws, but the gist of absolute 0 is that temperature is a measure of kinetic energy of molecules. How fast are they moving? How much energy do they have to move around, vibrate, spin, bop it, twist it, turn it, that sort of thing. At 0 Kelvin, molecules have 0 energy. And so that's just our definition for temperature is, at this point, everything is stationary. There's no kinetic energy. The temperature of that system would be 0. And then you go up from there. As molecules get faster, their Kelvin temperature increases. Turns out that where water freezes, this is its temperature in Kelvin, 273.15. Now, over here with Fahrenheit, Fahrenheit's a little bit weird. 1.8 degrees Fahrenheit is equal to 1 Celsius, or 1 Kelvin, because 1 Celsius and 1 Kelvin are the same thing. Not super practical, and also the whole thing about weird numbers. Like, same reason we don't want to use the imperial system. Weird numbers, right? We don't want to memorize all these crazy different conversions. So, for Celsius, 100 is easier to remember than 180, or 1.8 versus 1. So we don't care about Fahrenheit. We care about Celsius, but we also care about Kelvin. And the reason that Kelvin is going to be very crucial for us is because sometimes you have formulas. Let me not write this here because something's going to appear in that spot. Sometimes we're going to have formulas, not in this class, but later on, that have temperature involved. And if you input a reasonable temperature to do an experiment at, and by reasonable I mean you can access it, you can do an experiment at 0 Celsius, that's not hard. You end up killing your equation. Anything times 0 is just going to be 0. And even worse, if I do this to solve for, say, R, and now I try to put 0 here, bad things happen, right? You can't divide by 0. So, working in Celsius with mathematics, our relationships that we derive fall apart. So we can't use Celsius when we're doing calculations. We have to use Kelvin. Okay, so Kelvin is used in calculations. I realize you can't see the word Kelvin down here. Oops, don't want that to appear. I realize you can't see the word Kelvin because my picture is in the way, but we use Kelvin for calculations pretty much extensively. When we get to that in 162, you'll see that again, and we'll start working with Kelvin. Now, interestingly enough, I have this extra temperature scale here. So this temperature scale is the absolute value version for Fahrenheit. So we can set this down here. This would be 0 in this scale. But I need a letter for it. What letter should I pick? Anyone know what this scale is called? Let's see if we can add a little highlight to it. Hold on, let's see here. Oh, that's the wrong color highlighter here. Hold on. Oh my goodness, this interface. There you go. Which letter should I use? There we go. I think people just got the joke, right? All right. And you're exactly right. The letter that is used for this variable is... It's not U. No, it's R. This is what's known as the Rankine scale. Oh, that's kind of neat. There we go. So the Rankine scale is just the absolute value scale for Fahrenheit. But as far as we are concerned, we do not care at all about these two scales. These are dumb for our purposes. These two are the ones that we're going to use. And primarily of those two, we're going to try and use Kelvin the most. All right. Just in case you need formulas for these, here are the formulas. Honestly, though, if you're asked to convert temperature, and you will be on quiz number 3 because I have to give you something from this unit to do, just type it in Google. Type in 74 Fahrenheit to Celsius and hit enter, and Google will do it for you. There's really no reason to use these formulas. But just in case you wanted to, here you go. If you are looking in other sources, you might actually see this represented as 9 divided by 5. I have put these as a decimal just because it's easier to typeset 1.8 than it is to do a fraction. And then this over here is divided by 1.8, which is divided by 9 over 5, which is just times 5 over 9. So if you look at the formulas for those, and you see them elsewhere, and you're like, well, these have fractions. Wes has had 1.8. They're the same thing. The other important thing to note on here is that the definitions between Fahrenheit and Celsius are exact, because these scales have a 0 point that we have established just artificially. Like, we've defined the freezing point of water as 32 Fahrenheit and 0 Celsius. We just chose that arbitrarily. So any conversion between the two will be an exact number. But when you go to Kelvin, Kelvin has a 0 that is a physical constant, which is absolute 0. And our conversion between Kelvin and Celsius, therefore, is going to be approximate, because we can't set the 0 point for Celsius somewhere that will fall exactly on the Kelvin scale and still have it be a meaningful relationship. So for Celsius here, if you need more decimals, you could do this. So 273.145 is actually that number written to 3 decimal places. Generally speaking, most temperature probes and thermocouples that you would use that detect temperature, they only go down to 2 decimal places anyway. So just keep that in mind. You'll just chop your numbers right here when you do the addition. Use the addition sig figs rules and you'll be in good shape. This just talks about absolute 0. We've already talked about that, so you can rewind the lecture if you want to. I'm not going to make you do these examples because... Oops, sorry, it startled me. So we're going to skip that. You could do this as practice if you really want to convert temperatures. Like, that's fine. But that's all I got, so here you go. All right, that's the end of chapters 4 and 5. And I'm not going to start Unit 6 because we have like 20 minutes left, so that's all I got. So we'll end 30 minutes early. You can go and enjoy your dinner, enjoy the sunset, enjoy something else, right? I want to thank everyone for coming out to the lecture. Make sure that you get all those assignments in because the deadlines are closing. Quiz number 1 closes tonight. Lab worksheet number 1 is due tonight. It closes tomorrow. Quiz number 2 will be due next week. And when we come back for week 4, Unit 6 will go really quickly, so there will be another quiz coming out. And then we will work on Unit 7 and 8, and then it'll be time for exam number 1. So we are very quickly approaching midterms, believe it or not. So yeah, have a wonderful weekend and congratulations. You are a third of the way through Chem 140.